NASA regards Bennu as the most dangerous rock in the solar system. Its path through space gives it the highest probability of impacting Earth of any known asteroid. Despite the relatively high chances of Bennu's orbit intersecting with that of Earth in the next couple of centuries, most experts think the asteroid is rather harmless. But what will happen if it collides with Earth? Albedo is like a surface's reflectivity score. It measures how much sunlight bounces off compared to how much it hits. Think of coal. It reflects 10% of sunlight. The Moon, about 7%. Now the big space rocks, the ones we worry about hitting Earth, 78% of them reflect only 2% to 7% of sunlight. They're tricky to spot, like trying to find a small piece of coal in the vast darkness of space. On February 13, 2013, while space agencies assured us a 30-meter asteroid would safely pass by Earth, a different asteroid snuck in. It lit up Russia's skies with a dazzling show. But the beauty hid the danger. At 30 kilometers above Earth, it exploded, brighter than the sun, causing burns and chaos. The blast packed 30 times the power of the Hiroshima bomb, damaging thousands of buildings and injuring over 1,000. This Chelyabinsk meteor was only 20 meters wide, just a small fry in the world of near-Earth objects. Yet, it's these small ones that often create the biggest stir. Moving up the scale, we have the Tunguska-like objects, named after a 1908 event in Siberia. This was a monster, an asteroid about 30 to 50 meters wide. It flattened thousands of square kilometers of forest like a giant hand swiping trees away. The explosion was colossal, equivalent to thousands of atomic bombs. It's a reminder of the terrifying power of space rocks lurking just beyond our atmosphere. Large objects in space can cause major problems for Earth, ranging in size from small cities to entire planets. Think about the asteroid that led to the dinosaurs' extinction millions of years ago. This gigantic rock, measuring 10 to 15 kilometers across, crashed into Earth near modern-day Mexico, creating a crater larger than many countries and deeper than some oceans. The impact ignited continent-wide wildfires and triggered massive waves that swallowed coastlines. The debris thrown into the atmosphere blocked sunlight, plunging the planet into prolonged darkness and cold, making survival incredibly difficult for all life forms. Compelling evidence supports the catastrophic effect of this asteroid on the dinosaurs. A key clue is a unique layer of clay found worldwide, rich in iridium, a metal rare on Earth but common in space rocks. Fortunately, we monitor most large asteroids and have determined that none pose an immediate threat. However, smaller asteroids are harder to track and many remain undiscovered. Even when we find them, predicting their precise paths is complex and uncertain. Chaos theory significantly contributes to this uncertainty. Even minor changes can lead to significant consequences, and a small nudge to an asteroid's trajectory can result in disaster. Additionally, gravitational pulls from planets can alter their courses, complicating our predictions further, making it as challenging as forecasting the weather a century in advance. Beyond gravitational forces, other influences, such as the Yarkovsky effect, also impact asteroids. When sunlight heats one side of an asteroid, the side facing away from the sun cools and releases the heat as infrared radiation. This uneven heat release creates a slight push, gradually altering the asteroid's path over time. Potentially hazardous objects, PHOs, are space rocks that orbit close to Earth and are large enough to cause significant damage upon impact. We've identified and mapped over 2,500 of these objects, but many more remain undiscovered. So, what if we detect one heading our way? Take Bennu, for example. Bennu is a time capsule from the solar system's early days, over 4.5 billion years old. This asteroid is rich in carbon-based molecules, which may be linked to the origins of life. Studying Bennu could reveal vital clues about how life began on Earth. Bennu's orbit occasionally intersects with Earth's path. It's a massive asteroid, about 490 meters wide, comparable to the Empire State Building's height, and weighs roughly 73 million metric tons, equivalent to 13 Great Pyramids of Giza. If Bennu were to collide with Earth, the impact would be catastrophic. Traveling at around 28 kilometers per s, 63,000 miles per hour, a collision would release energy equivalent to over a gigaton of TNT, 200 times stronger than the Tunguska event or 200,000 times the Hiroshima bomb. Bennu has a notable chance of hitting Earth in the late 22nd century, with a 1 in 2,700 probability between 2175 and 2199. Although these odds seem low, a minor miscalculation could turn a near miss into a disaster. Space agencies like NASA are already developing strategies to mitigate potential asteroid threats. One significant challenge is deploying the necessary technology to the right place. In 2016, NASA launched the OSIRIS-REx mission aboard an Atlas V rocket from Cape Canaveral Air Force Station. Its mission was to rendezvous with and study Bennu. Instead of a direct flight, the spacecraft used a gravitational slingshot around Earth in 2017 to align itself with Bennu's path. OSIRIS-REx traveled over 2 billion kilometers and required trajectory correction maneuvers, TCMs, to reach its destination. In late 2018, it slowed down to match the speed of the asteroid Bennu and started orbiting it, providing NASA with valuable skills for future asteroid navigation. Contrary to movies like Armageddon, using nukes to destroy asteroids is not straightforward. In 2021, Lawrence Livermore National Laboratory tested the impact of a nuclear explosion in space on an asteroid. Without air to carry the blast wave, the explosion releases energy that can push the asteroid, but not as powerfully as on Earth. The surface of the asteroid would experience intense heat and energy, vaporizing parts of it and causing a recoil effect. However, this explosive force isn't just a gentle push. It can break the asteroid into large chunks, which may still pose a threat to Earth. Small asteroids around 100 meters wide or less could be disintegrated with a special nuclear bomb, but larger asteroids remain a challenge. Some asteroids are like rubble piles held together by gravity rather than solid rock. To redirect these, NASA's DART mission tested smashing into a rubble pile asteroid, targeting the moonlet Didymos B, part of a pair orbiting the larger asteroid Didymos. If a spacecraft zooms toward Didymos B, speeding at a crazy 6.6 kilometers per second, boom, it crashes into the little moonlet. And guess what? After the dust settled, Didymos B's orbit changed. The time it took to circle its big buddy dropped by a whopping 32 minutes. That's proof that slamming into rubble piles can really shake things up in space. Now, there are other ideas floating around, like blowing up asteroids from the inside or using fancy machines to push them away. But there's a snag. Getting close enough to drill into an asteroid is no easy feat. Pushing on it could even send the spacecraft tumbling away. Space rocks aren't the most stable surfaces to anchor to after all. Since we have observed the scientific angle on the possibility of stopping Asteroid Bennu, what are your thoughts about it? Comment down below and check out the next video from the I button, which is another great observation for space science. Hit that subscribe button to get more videos to increase your knowledge about the space.